Hello everyone, this is section 6.6, inverse trig functions. Let's start with the sine function. So the sine function is not one-to-one, but we may restrict its domain. If you picture the graph of y equals sine x, or even y equals cosine x, it's just that wave function, so it's not going to pass the horizontal line test. So that's why we're going to restrict its domain. So again, the sine function is not one-to-one, but we may restrict its domain. It's negative pi over 2 to pi over 2 to make it one-to-one. So we'll just make a little sketch of the graph here. So this will be the graph of y equals sine x, just over this domain here. So here's pi over 2, negative pi over 2. If you recall, sine x, y equals sine x only reaches as high as positive 1 and as low as negative 1. So sine goes through the origin. Sine of pi over 2 is 1. Now if we went to sine of pi, we're going to be back here at 0, and then that's not going to pass a horizontal line test. Sine of negative pi over 2, which is the same as sine of 3 pi over 2, that's going to be down here at negative 1. And then we have the curve that goes like this. So we define the inverse of sine x. It's written like this, which is also equal to arc sine of x, which we're just going to call y. And then this implies, especially if we go over here to the inverse of sine x is equal to y, then we could rewrite this as sine of y is going to equal x. So if we just took the sine of both sides, sine and sine inverse, depending on the situation, are going to cancel. I'm going to show you that in a little bit. And then we would just take the sine of y. So x is going to equal sine of y. And y is in between negative pi over 2 to pi over 2. So if x is in between negative 1 to 1, so you see if all I'm doing here is switching the x and y's. So right now the range of y equals sine x is going to be negative 1 to 1, but then that's the domain of our inverse. Our domain of y equals sine x is negative pi over 2 to pi over 2, and then that's going to be our range over here for our inverse. All right, so if x is in between negative 1 to 1, then arc sine x is the number y that's contained in this closed interval from negative pi over 2 to pi over 2, such that sine of y is equal to x. So again, when we find arc sine or inverse sine of a value, it returns an angle value. So let's take a look at some examples. Now for these problems, it's going to be very helpful to just review the unit circle. So again, I'm just going to make a quick sketch of the unit circle. So this is what we're working at. Our values for sine inverse of x can stay between negative pi over 2 and pi over 2. And that's what this is saying right here. So it's x, as long as x is between negative 1 and 1, which is along our x-axis here. So if we picture positive radical 3 over 2, down here radical 3 over 2 is going to be negative for our y value. Because remember, sine is always the second number of the ordered pair. So we're looking in our first quadrant right here. So for radical 3 over 2 to be our second number, let me just revisit our ordered pairs here. So we have 30 degrees is pi over 6. The ordered pair here, if we're creating a right triangle, we go over the longer leg. So there's our radical 3 over 2, and then a positive 1/2. When we're right in the middle at pi over 4, we have the same two values in the ordered pair, radical 2 over 2. And then when we're up here, it's just a rough estimate here. This is, let me move this pi over 2 out of the way. This would be 60 degrees, or pi over 3. And then this is the ordered pair. We go over the shorter leg and up the longer leg. So 1/2 radical 3 over 2. So to answer this question, we're looking to see where we have a positive radical 3 over 2 for a second value, and that happens at pi over 3. And that's how we're using this. Again, arc sine returns an angle value. Pi over 3 radians is an angle value. Let's take a look at another example. This one's going to be cosine of arc sine of 3/5. This one we can't use the unit circle for. 3/5 is not a value on the unit circle, so we have to think of this a slightly different way. And what we're going to do here is we're going to create our own triangle. So I'm going to think of this as the inverse sine for arc sine of 3/5. Inverse sine of 3/5. I'm going to let that equal theta. So then I could rewrite this. Sine theta is going to equal 3/5. Let me put that in parentheses here. So now I'm just going to go over, and again, this has to be in the first or second quadrants. I'm just going to make my right triangle here. So here's theta. So sine is opposite over hypotenuse. So across from theta, this is my opposite, so that's going to be 3. That's my hypotenuse, so that's going to be 5. And then if I use the Pythagorean theorem, I could write this, the length of this side, as the square root of my hypotenuse. So 5 squared minus 3 squared. So in other words, I would just say 3 squared plus x squared is going to equal 5 squared. So x squared is going to equal 5 squared minus 3 squared, and x is going to equal the square root of 5 squared minus 3 squared, which is 25 minus 9, which is the square root of 16, which is 4. So now I can go back up, and if I call this whole thing theta, now I'm just finding cosine of theta, and cosine is adjacent over hypotenuse, so then this just equals 4/5. So in this case, I just had to complete a right triangle. Sine turned out to be positive, so I knew I was in the first quadrant, because if I'm in the fourth quadrant, sine would be negative. All right, so let's take a look at some cancellation equations. So if we have arc sine of sine of x, remember arc sine is just the same thing as sine inverse, and inverses cancel. So this is going to equal x as long as x is in between negative pi over 2 to pi over 2. And then vice versa, if we took the sine of arc sine x, that's also going to equal x, if x is between -1 to 1. So it all depends on what's inside the parentheses, because arc sine we have to stay between negative pi over 2 and pi over 2. But here, to take the sine of something, we have to stay between -1 and 1. So let's take a look at an example using these cancellation equations. Now we could still piece it together like we just did in the last problem. There's nothing wrong with that. So in this case, if you notice, I'm taking sine of pi, so that looks like the first one, arc sine of something here. But as long as x is between negative pi over 2 to pi over 2, and this isn't, so in this case, we're just going to go ahead and find this first. So sine of pi is going to be 0. So then this becomes arc sine of 0. Now again, picture the unit circle. If we're at a y value of 0, we're at the ordered pair 1, 0. So if we look at the unit circle, if we're right over here, again, we have to stay between this point and this point. So right here, we're at the point 1, 0, and that's what we're looking at. And then that's at 0 radians, so then that's just going to equal 0. Okay, so let's try this one. Next, we have arc sine of negative pi over 4. So negative pi over 4 is on the unit circle, and that shows up right here. We're going just pi over 4 radians in this direction. So this is negative pi over 4. This would be the ordered pair of positive radical 2 over 2 and negative radical 2 over 2. So sine of negative pi over 4 is negative radical 2 over 2. So now this becomes arc sine of negative radical 2 over 2. And then that just takes us back here. So if I'm looking at negative radical 2 over 2, that brings me back to negative pi over 4. So this, in fact, was a cancellation equation because negative pi over 4 was between negative pi over 2 and positive pi over 2. The arc sine and sine just cancel out, and I'm left with negative pi over 4. So next, let's come up with the derivative for the inverse sine function. Here we're going to take a look at a theorem. All right, so this is saying, and we're just going to show a proof here, the derivative of arc sine x, or sine inverse of x, is 1 over the square root of 1 minus x squared. And again, at the end, I'll generalize this for u of x. As long as x is between negative and positive 1. So our proof, we're going to let y equal arc sine of x. Then we can rewrite this as x is equal to sine y. So then the derivative of x, again, we're just using implicit differentiation here. We're just going to take the derivative of both sides, becomes the derivative of sine of y. Derivative of x is just 1. Derivative of sine of y is going to become cosine y times y prime. So then y prime, I'm just going to divide both sides by cosine y, becomes 1 over cosine y. But a couple things. We want to rewrite this in terms of x. And then to show that it's going to equal this result right here, we're going to use a little trig identity. So it's a Pythagorean identity where we'll say sine square y plus cosine square y is going to equal 1. And then I just want to solve this for cosine y. So I'm going to subtract sine square y from both sides. So cosine square y is going to equal 1 minus sine square y. And then I'll take the square root of this. Now the reason we only keep the positive square root is if we were to actually sketch the graph of y equals sine x, all of our derivatives are going to, all of our slopes of our tangent lines are going to be positive. Or rather, the graph of y equals the inverse sine of x. All of our derivatives, slopes of our tangent lines are going to be positive. So we only keep the positive square root here. So now y prime is going to equal 1 over the square root of 1 minus sine square y. And then we could rewrite sine square y as y prime is equal to 1 over square root of 1 minus sine y squared. If we go all the way back up to the beginning here, sine y is equal to x, and that's what we want. We want to get this in terms of x. So now y prime is going to equal 1 over square root of 1 minus x squared. And there's our derivative. All right, so to generalize, we'll say if y is equal, and I'm going to use the inverse sign, but it could be arc sine as well. We'll say inverse sine of u of x, then y prime is going to equal 1 over the square root of 1 minus u of x squared times u prime of x. So again, I just want to graph side by side both of these functions. Y equals sine x again like I did at the beginning, and then y equals the inverse sine x. All right, so here again is the graph of y equals sine x. Again, when I started with just stopping it from negative pi over 2 to pi over 2. So now we're switching our x's and our y's. So this is where x is between negative 1 to 1, and y is between negative pi over 2 to pi over 2. So we still have 0, 0. Over here we have the point pi over 2 and 1, so here we're going to have 1 and then pi over 2. And then here we have negative pi over 2, negative 1, so we have negative 1, negative pi over 2. And remember, think of the reflection over the line y equals x, so it's not going to have the same curve here. It's actually going to be switched around a little bit. So it looks like this. But this is what I'm talking about. When we draw in tangent lines, the slopes of all of these tangent lines are positive. So that's why we were going just with the positive square root. All right, let's take a look at an example. So let's take the derivative of arc sine of x squared. If you want to pause the video to try this on your own, please feel free. All right, so first we need to apply the chain rule here. So this 2 is going to come down in front. So this becomes 2 times arc sine of x, really to the 2 minus 1, so it's to the first. Then times the derivative of the inside, so now this is our new rule, becomes 1 over the square root of 1 minus x squared. Let's try another one. Y equals, we'll do arc sine of 3x to the fourth. Let's find y prime. Again, if you want to pause the video, try this on your own. All right, so y prime is going to equal, first we start with the derivative of our arcsine function here. So we're going to have 1 over the square root of 1 minus 3x to the 4th squared, then times the derivative of 3x to the 4th, so we'll get 12x cubed. You could simplify what's inside here a little further. So we say 1 minus 9x to the 8th. Now if we had to do more with it, we would try to simplify a little further, but this is good enough for right now. So next, let's take a look at the inverse cosine function. Again, I'm going to start with a graph. We're going to graph y equals cosine x, and then we'll graph its inverse. So for the graph of y equals cosine x, I'm actually just going to start at 0 and then go to pi for this to be 1 to 1. All right, so again, cosine is going to start not at the origin. It's not going to go through the origin. It's going to start up here at 1. And then at cosine of pi over 2 is going to give us 0. Cosine of pi is -1. And after that, it's going to start to come back up. So then this would no longer be 1 to 1. So I have to go just from 0 to pi. That looks like this. So we could say the domain of what I just have graphed here is from 0 to pi. And the range is from -1 to 1. So then the graph of the inverse cosine of x my domain here, what x is going to go from is from -1 to 1, and then from 0 to pi. I'll still put in pi over 2. So right here, when I have the point 0, 1, now I'm going to have 1, 0. When I have the point pi over 2, 0, I have 0 pi over 2. And then I have pi -1, so we're going to have -1 pi. So this is what the graph of y equals cosine inverse of x looks like. Now, if we were to draw on tangent lines here, all of their slopes are negative. So that's what's going to help us when we go to show the proof for this. Okay, so here our domain goes from -1 to 1, and then our range is from 0 to pi. So you can see because they're inverses, the domain and range is just switch. So some cancellation equations here. Let me first also write this out just below. So we could write that the arc cosine of x is equal to y. Can also be rewritten as x equals cosine y, or cosine y is equal to x. And again, y is staying between 0 and pi. When we're looking at this version of it, as well as the outputs here. All right, so cancellation equations, we'll have arc cosine of cosine x is going to equal x for all x values in between 0 and pi. And then cosine of arc cosine x is going to equal x for all x values between -1 to 1. All right, let's take a quick look at the inverse tangent function graphically, and then actually instead of proving any more of these, we'll just write them out generally. A lot of the proofs are done just how we did for the derivative of arc sine of x. So now let's take a quick look at inverse tangent function. And again, we could start by saying arc tangent of x is equal to y. Can be rewritten as tangent y is equal to x. And in this case, it's not going to include the pi over 2's, but y is strictly between, so just greater than negative pi over 2 and less than pi over 2, not equal to them. And this is all done by the graphs. So if you recall the graphs of y equals tangent x, and even cotangent, but we'll focus on tangent, there's vertical asymptotes throughout. And then this happens at negative pi over 2 and then pi over 2. Because tangent of both of these values is undefined. Now tangent of 0 is 0. Tangent of, we'll say pi over 4 halfway in between, that's going to be a 1. And then tangent of negative pi over 4 is going to be negative 1. So what we have is we start to get really close to this asymptote, go up through, pass through 0. So then it looks like this. But it never touches the graph at those asymptotes, so that's why we can't include the pi over 2's. So here the domain is really going to be all real numbers except these pi over 2 values. So we're going to write this, we'll just say all reals except x equals, and it's going to be pi over 2, 3 pi over 2. Actually, with this one, we'll just stop it here instead of writing it out for the entire graph. So in this case, the domain will just go from negative pi over 2 to pi over 2. We'll use parentheses here because we're not including them. And then the range is going to be all real numbers. So now if we go to reflect this over the line y equals x, now our y values just go from negative pi over 2 to pi over 2. That's what we're saying right here. And then here we're going from negative 1 to 1. So now we'll have our horizontal asymptotes instead of vertical. We'll go here and here. Again, as we go to graph this, this is what it's going to look like. And you can see now the domain is going to be all real numbers, and our range is from negative pi over 2 to pi over 2. And this is for y equals the inverse tangent or arc tangent function. All right, so what I'm going to do on the next page, I'm going to go ahead and list out all of the trig derivatives and then their inverses. So this will be very good just to keep on a separate sheet of paper as a nice reference sheet. So first I'll list out the derivatives of the 6 trig functions. I'll just write it this way. If y is equal to sine of x, y prime is equal to cosine x. 2, I'm going to jump to tangent. If y is equal to tangent x, y prime is equal to secant square x. And then 3, if y is equal to secant x, y prime is equal to secant x tangent x. Now keep in mind these all apply to the chain rule applies, so whatever x happens to be, you still have to take the derivative of it. What I'm going to list over here, now I'll go if y is equal to cosine x, y prime is equal to negative sine x. If y is equal to cotangent x, y prime is equal to negative cosecant square x. And if y is equal to cosecant x, y prime is equal to negative cosecant x cotangent x. So the reason I have the 4, 5, and 6 listed separately in its own column, because if you notice, all of their derivatives are negative. Everything for 1, 2, and 3, those derivatives are positive. Also for 4, 5, and 6, these are all the trig functions that start with a c: cosine, cotangent, and cosecant. So that's a nice, easy way to get a good visual to remember those. Now let's take a look and make a list of the derivatives of the inverse trig functions. And we'll list them the same way here. So I'll write it this way. I'm just going to use arc of each one. So we'll have arc sine of u of x. For these, I'm going to put in the u of x, so it's easy to remember here. So this is going to become 1 over the square root of 1 minus u of x squared times u prime of x. Then we'll do the derivative of arc tangent. Actually, this first one, I'll just use the u of x. It'll be a lot easier to remember them with x's. Just know that the chain rule still applies. This actually becomes 1 over, no square root here. It's just 1 plus x squared. Again, times whatever the derivative is of x, that is. And then we'll do secant, arc secant. This becomes 1 over x times the square root of x squared minus 1. And again, times whatever the derivative of x is. So notice all three of those, the sine, the tan, or arc sine, arc tangent, arc secant, those are all positive. Now let's get to the negative ones. So then we'll have the derivative of arc cosine becomes just the opposite of what sine is. Negative 1 over the square root of 1 minus x squared. Derivative of arc cotangent is just the opposite of tangent. So here we just get negative 1 over the square root of, no square root, 1 plus x squared. And then we'll go with arc cosecant. And then that just becomes the opposite of arc secant. So negative 1 over x times the square root of x squared minus 1. So keep that list handy. Keep looking over them. So let's do some more examples. We're going to talk about some limits as well as integrals. So let's let y equal arc tan of x squared plus 1. Pause the video, go back to the list, and take a second to figure out what this derivative is going to be. All right, so again, we're looking at arc tangent. So y prime, remember this one's positive, is going to be 1 over, and then it's 1 plus whatever quantity this is squared. So we're going to write this as x squared plus 1 squared. And then times the derivative of the x squared plus 1, so then it's just times 2x, and we can leave it just like that. All right, so let's talk some limits here. And again, it's helpful to picture the graph, which is why I went over and graphed the inverse of sine, inverse cosine, and then inverse tangent. So let's say the limit as x approaches infinity of arc tan x. So let's go back to the graph. So we're looking at this graph over here, y is equal to arc tan x, or the inverse tangent of x. So as x keeps increasing without bound, we have this horizontal asymptote up here. So as we keep going this way, our graph is just getting closer and closer to the value of pi over 2. So that's what that's going to become. And then the limit as x keeps decreasing without bound of arc tan x. What do you think that's going to equal? That's going, as we keep going to the left, we're going to go down to negative pi over 2, but we don't get any lower than that. So now, let's find the limit as x increases without bound of arc cosine of 1 plus x squared over 1 plus 2x squared. Now for this, we're going to say since arc cosine is continuous, we could rewrite this at the limit as x approaches infinity of arc cosine of this quantity. We could rewrite it as arc cosine of the limit. So then this becomes arc cosine. Now because the degrees are the same, I'm going to write this out off to the side. So if we're taking the limit as x approaches infinity of 1 plus x squared over 1 plus 2x squared, we could do that little manipulation here where we divide everything throughout by x squared. If we do that, we're just going to be left with a 1/2. Or the shortcut here is if our degrees of the numerator and denominator are the same, we just end up dividing the coefficients. So that's going to become a 1/2. So now we're picturing the unit circle. Remember cosine, we're looking between 0 and pi. So we're right up here to figure out our angle measure. So where is cosine going to be a positive 1/2? And cosine is positive in our first quadrant, and it's 1/2 here at pi over 3. So arc cosine of 1/2 is going to equal pi over 3. So we're right up here. All right, let's take a look at inverse trig integrals. I'm just going to write out a couple here. So if we're looking at the integral of 1 over the square root of 1 minus x squared dx, again, we just go to our list of the derivatives of inverse trig functions. This one matches the derivative of the inverse sine. So this is just going to equal arc sine of x plus c. And if we have the integral of 1 over 1 plus x squared dx, again, both of these are positive. So there's no square root here, so this becomes arctangent of x plus c. So let's finish this up with just 2 examples of integrals. So let's find the indefinite integral of e to the 2x over the square root of 1 minus e to the 4x. And then before x squared dx. All right, so obviously we're going to use a use substitution here. We've got quite a bit going on. So notice, if you could recognize, this is something over the square root of 1 minus something, and it does look like if we square the 2x, we'll get the 4x squared. So we're going to let u equal e to the 2x. And then du over dx is going to equal e to the 2x times 2. So then if I solve this for dx, we'll just say du is going to equal dx is going to equal du over 2e to the 2x. So now we'll come back over here. This becomes the integral. I'm going to leave the e to the 2x at the top. And then this is over the square root of 1 minus u squared. Again, dx is du over 2e to the 2x. So now you can see the e to the 2x's divide out. We'll put the 1/2 out in front, so it's 1/2 times the integral of 1 over the square root of 1 minus u squared du. And just like our last example, right here, that is the derivative of arcsine. So the antiderivative of this is going to become our arcsine here. So we'll have 1/2 times arcsine of u plus c. Then we just bring back in what u is equal to. So 1/2 arcsine of e to the 2x plus c. Okay, let's do one more. Integral of 1 over x squared plus 4 dx. So before we do anything else, we kind of have to do an algebraic manipulation here. So what I'm going to do, because right now it doesn't look like the form of, it looks closest to tangent, but this isn't 1 plus an x squared, but I could get that by factoring out a 4. So if I do that, if I factored out a 4, then this would become x squared over 4, and then plus 1. So now I could take out that 1/4, and now I have 1 over 1 plus something squared, so I could rewrite this as x over 2 squared. That will give me x squared over 4. And now I could let u equal the x over 2, and then du over dx is just going to equal 1/2. So I'm going to multiply both sides by 2 here, so dx is going to equal 2 du. So now as I go to rewrite this, I'll get 1/4 the integral 1 over 1 plus u squared times 2 du. So I'll bring that 2 out, so the 2/4 will just give me a 1/2. And now the antiderivative here is the arctangent. So we get 1/2 times arctangent of u plus c. And then we'll just bring back in the x over 2. So 1/2 times arctangent of x over 2 plus c. So as always, guys, let me know if you have any questions over this section. There's a lot of formulas to get used to here.